Hello, my name is Robert Neville, and today I will be doing a Wireshark frame analysis. I'm going to break down two wireless frames captured in a PCAP file and show how they relate to the OSI model, specifically the data link, network, transport, and application layers. Understanding how to read frames at each layer is a core skill for anyone entering IT or cybersecurity. It helps you troubleshoot network issues, understand how devices communicate, and recognize why encryption is so important to protecting data. Before we start, it's important to understand why Wireshark is such a critical tool in IT. Wireshark gives us a visual way to see how devices communicate across the OSI layers. Instead of guessing what's happening on the network, we can actually observe it frame by frame, packet by packet. It's also one of the most valuable troubleshooting tools we have. Whether you're dealing with slow performance, dropped connections, or suspicious traffic, Wireshark lets you pinpoint exactly where the issue is occurring. Now that we understand why Wireshark is such an important tool, let's take a look at the file we will looking at. Potentially, you'll see hundreds or thousands of frames. Today, we're going to be looking at frame 8 and frame 136. They show two very different situations. On the left, we have frame 8, which is an unencrypted 802.11 data frame. Because it's unencrypted, we can see everything: the MAC addresses, the IP information, the TCP ports, and even the actual text data being transmitted. This gives us a full view across multiple OSI layers. It's the hacker's dream. On the right, we have frame 136, which is an encrypted data frame. Here, the only thing we can clearly see is the layer 2 information. Everything above that, the IP addresses, the ports, and the application data, is completely hidden because of wireless encryption. These two frames make a perfect comparison. Let's start with frame 8, the data link layer, or layer 2. This is where we look at the MAC addresses, the physical identifiers that allow devices on the same network to communicate. In this frame, we see the source MAC address and the destination MAC address. They're underlined in red. These addresses are burned into the hardware and they're essential for local delivery. Switches and access points rely on these MAC addresses to decide where to forward each frame. So in this unencrypted frame, we get full visibility into the MAC information, which makes it easy to trace exactly who's talking to whom at the physical network level. Next, let's move up to layer 3, or the network layer. This is where we start looking at the IP addresses that identify the logical endpoints in the communication. In frame 8, we see the source IP address and the destination IP address. They're underlined in red. Unlike MAC addresses, which only work inside the local network, IP addresses allow devices to communicate across different networks and subnets. This is the layer responsible for routing, making sure the packets take the correct path to reach the right destination. So while layer 2 gets the frame to the correct physical device, layer 3 ensures the packet reaches the correct network location. In this unencrypted frame, we can clearly see both IP addresses, which gives us full visibility into who is communicating at the logical network level. Now let's move up to layer 4, the transport layer. This is where communication becomes application specific. Because various ports are used to identify which process or service should receive the data. In frame 8, the source port is TCP port 20, and the destination port is TCP 1105. The IP addresses get the packets to the correct device, but the port numbers tells that device which application should handle it. This is what allows multiple programs like email, web browsers, YouTube to communicate over the network at the same time without interfering with each other. Layer 4 is also responsible for managing reliability and flow controls. Since this is a TCP traffic port, the connection is using acknowledgements to ensure the data arrives correctly. In this unencrypted frame, we can see all of this information clearly, which gives us full visibility to the transport layer communication. Finally, at the top, we reach layer 7, the application layer. This is where user-facing applications operate, and it's also where we can see the actual content being transmitted. Because frame 8 is completely unencrypted, Wireshark is able to display the raw text inside the payload. In this case, the data includes the phrase, "These are the times that try men's souls." This is a perfect example of why encryption is important. Anyone capturing traffic on this network would be able to read the user's data in plain text with zero effort. Layer 7 is all about delivering meaningful information to applications, but when that information isn't protected, it becomes a major security risk. Now we're moving on to frame 136, which is encrypted, but even with encryption, layer 2 information is still visible. Encryption protects the payload. That's by design, because the network still needs to know where to physically send the frame. The source MAC address and the destination MAC address are underlined in red. These addresses identify the devices involved in the communication, and they're essential for switches and access points to forward the frame correctly. This is a great example of how different OSI layers serve different roles in network communication. In this slide, we're looking at why layers 3 and 4 are completely missing in frame 136. In an unencrypted frame, this is where we normally see the source and destination IP addresses along with the TCP or UDP port numbers. That information usually appears right after the wireless headers where I've circled in red, but because this frame is encrypted, all of that upper layer data is hidden inside the encrypted payload. Wireshark can still show us the structure of the frame, but it can't decode anything above layer 2 without the proper encryption keys. This is exactly how wireless security is supposed to work. Encryption doesn't just protect the application data, it also protects the routing and transport layer metadata. That means an attacker capturing this traffic wouldn't be able to see who the device is communicating with or which service or application is involved. All of that information stays protected, which is a major improvement over unencrypted wireless traffic. Here in frame 136, we're looking directly at the encrypted payload. Unlike frame 8, where we could clearly read the application layer text, this frame shows nothing but scrambled hexadecimal data. It's exactly what we want to see in a secure wireless environment. Payload is completely unreadable without the correct encryption key. Even though we can capture the frame, we can't read any of the information inside above layer 2. Above layer 2 is fully protected. Encryption ensures that even if someone's monitoring the network, the data remains secure and unusable. Comparing this to the unencrypted frame highlights the difference between exposed traffic and properly secured traffic. As we wrap up this presentation, there are a few key points I would like to highlight. First, frame 8 gave us full visibility across layers 2 through 7. We were able to see the MAC addresses, the IP information, the ports, even the application layer text. It's a clear example of what unencrypted data looks like and why it can be a major security risk. In contrast, frame 136 showed us the opposite scenario. Because the traffic was encrypted, everything above layer 2 was completely protected. The IP addresses, the ports, and the application data were all hidden inside the encrypted payload. This demonstrates exactly how encryption safeguards both data and metadata in wireless communication for personal information and for big and small organizations. Thank you for your time.